So I'll do my best to describe it. I'll wind up talking more about the parts I know more about, sort of automatically, but we'll take a look at what it means. So I'll start by motivating the problem. So why did we feel we needed a framework? Well, and this won't be news to the people here, but always good to think about it again. The world is awash in data. Your favorite set of V's will do. Science has gone from articles to data, the fourth paradigm. It's not just science, commercial data. We've gone from accounting systems to real-time supply chains and various other things. And you'd think all this data would yield better science and engineering and more commercial efficiency. And to a degree it has, although it's also had some unpleasant side effects. Data is hard to understand, share, or reuse across silos in which it starts. Again, this echoes stuff that Rob had just said, which is that just making, or maybe that was some other meeting I was in, but just making the data available is not sufficient. We need lots more magic. First of all, numbers are not self-explanatory. They come with a specific context, and it's hard to find data. You know, doing a search on 372 isn't particularly useful. You need other ways to locate data than what we've done with text over the years. And once you get it, how do you know what you can do with it? What does it mean? And how do you know if you can trust it or not? Science has a reproducibility problem. And as the data gets more complex and there's more of it, we spend more time on the data than we do on the science sometimes. And this is a point I'll hit multiple times during my short talk, which is current data will remain significant long after the technology changes fundamentally. Anyone who tells you that they know how computing and information management techniques will work 50 years from now doesn't know what they're talking about. And anyone who believes that the data that's collected today and the conclusions that we come to today will not be of relevance 50 years from now is equally ignorant of history and the way things move. So we need to attack these problems at a very fundamental level. And the solutions are not found in our current common internet or web standards. They just aren't there. So there was this meeting, and I'll put it in historical context a little later. And some of the people in this room, this virtual room, were in that meeting. And we came up with a joint declaration at a very high level, very general principles. And I'm going to share some of them here. We had a motivated need for a framework, a very general statement of my first slide, which is science and innovation are increasingly dependent on complex data and on machines to analyze it. Key is machines here. There's simply too much data for people to do what they normally do, we have done historically with data. There's too much of it, and we're missing lots of opportunities. So that means we need to design and develop a large integrative infrastructure for the tsunami of digital artifacts that are now populating the internet. And it's not that people aren't trying to do this now, but it's led to the emergency and mixing. Creolization is one word where you take things from different parts, different languages in the original meaning and put them together. A lot of tools, standards, interfaces. The person I work with describes it as, many APIs, and you don't know which one to use necessarily. You can't learn them all. Now, historically, there's a point at which to attack complexity, and that's the hourglass strategy, where you look for a convergence mechanism that's minimal and allows maximum flexibility for on either side of that narrow neck. Another way of saying this is low barrier to entry, but this has been commonly used to explain the success of the internet. And there are 100 different versions of this hourglass picture. I made one a while ago that put persistent identifiers in the middle. But this is an attempt to explain how the internet came together in one way, which is people could have physical, medium, and low-level network strategies of various kinds. But if they all agreed on IP, which is the internet protocol, the address scheme, and they all agreed to support that, and then everyone who built on top of that, the applications, agreed to support that, they could come together. And that turned out to be successful and has been successful for, going on 40 years. And there's another point when you look at this. You could also think of the resources and personnel needed to implement this. There are probably literally millions of web developers around the world today. A relative handful of people are necessary to keep that middle thing going in the right way. So it's highly efficient. So you have minimal convergence for maximum flexibility. You can keep expanding both of those top and bottom things as long as you keep the neck narrow. So what does that mean about developing a framework? So the group had come together actually from different technical backgrounds, and looking around had, I seem to be verifying a file, excuse me. Years of discussions in various venues led to the FAIR principles, which we'll look at in a little more detail in a few slides. So that was agreed to be an essential element of this convergence process. Agree on that. And agree on the notion of digital objects, where you take, this is an architecture more than anything else, which you take abstraction, stable binding, encapsulation, things we've known in computing for a long time, in an attempt to control complexity, not just computing, with abstraction. I'll try and hit that a couple of points along the way. Abstraction is a common way to deal with complexity. You abstract details into something that's easier to deal with and understand. And at the same time, we saw that the digital object concept was also compliant with the FAIR principles and was silent on semantic relationships, so they could be put together. And those were the three things that came together conceptually, leading up to that meeting and then confirmed in that meeting by a larger group of people. You could look at it like this: digital object architecture, semantic relationships, FAIR principles. That was sort of a historical take, by the way, coming together for a FAIR digital object framework. That's a very simplistic look at it, but that's basically what we've been talking about. So here's the timeline for this sort of thing. This was put together, as you can tell, in 2019, which is when the last time we talked about it as a group, really. So the digital object architecture stuff, starting with Bob Kahn and Bob Lewinsky, actually it was before 1995, that's when they wrote the article, talking about digital objects, and RDA has taken this up fairly extensively. Linked data platform, semantic web, putting semantics into all the linking and digital artifacts we have now. That was the Go FAIR take on that. M for M is metadata for machines. And then FAIR itself. The FAIR principle, EOSC, we just heard EOSC mentioned, Go FAIR. Now there'd be other people would put different dates on this probably, and different elements, but I think this is fundamentally a decent overview of what's been happening. So I will discuss each of these three phases, but the one I know the best because I've been involved in it is digital object architecture, so I'll start there. So the point of digital object architecture is to develop a data-centric infrastructure at a new level of implementation neutral abstraction. It's an architecture in the sense of multiple implementations would be possible to address that architecture and follow that architecture. And it has a few principles. Everything in the environment is a digital object. That's the first simplification. All you're dealing with is digital objects. Everything else has been abstracted away into digital objects. For basic information management tasks, you can treat every object the same, regardless of the content. You want that as well. You don't want to have to deal with something full of astronomy data differently than something full of biology data at the level of basic management, move, delete, create, etc. Every object has a globally unique and actionable identifier. You can't manage stuff that you can't name. You have to be able to name it and point at it. Every object has a defined registered identified type. You have to know what kind of a thing you're dealing with. Every object has tightly associated metadata. You need information about the entity. You need context. And every object has a queryable set of operations that could be performed on it. That's one of the keys here. And that's one of the abstractions that will allow objects, if we do it right, to survive into the future. We don't care how they're made. We just need to know what they can do. And you want to treat every information in the object the same until you have to differentiate among them to accomplish your purpose. This is extremely important and is successful across a number of domains. Internet packet routing is a favorite example. The internet is very good at moving packets around. And one of the reasons it's very good at moving packets around, or rather the people who manage the networks are very good at moving packets around, is because you don't have to worry about what's in the packet. It's just a packet. You don't have to look inside. So that's very efficient. Looking inside and dealing with the insides is the business of the node where the packet ends up. File systems, possibly more familiar to a lot of people, are the same way. You don't have to care where your bits are stored. You just need a name of a file. You invoke the name. The operating system lets you do that. And that the resources and personnel that I was talking about with the narrow neck of the internet hourglass applies here as well. There are a handful of experts who create file systems and know where the bits are stored. And then there are many, many, many more developers who just assume that when they call a file, the bits will be gathered up, whether they're in the cloud or moved from ancient floppy disk 10 years ago to a spinning disk to a cloud service over to it's still a file, and they don't have to worry about that. And we want to define information objects by function, not format. Here the analogy is object-oriented programming, which befuddled me when I first encountered it. Being someone who wanted to know how everything worked, I thought, what do you mean information hiding? You don't want to tell me how that works? But of course you don't want to know how a function works. You just want to know how to interact with it. That way the function can change. This is minimally exposed functionality. You just want to know what something can do. And then this allows you to functions to survive changes, information objects to survive changes. This architecture is silent on semantics, metadata, schemas, etc. It's at a different level. It's at the architecture level, not the meaning level. And again, this is the last time I'll say it, new approaches must enable data to outlive current technology. What we're doing now will be important going forward. You know, what will be lost, what will be saved. This is a picture I drew many years ago. It's a very general, idealized view of this notion. Going from right to left, you have data stored in various ways, entire information systems, if you will, a set of services in between, and the result is a set of persistently identified, virtually aggregated digital objects, including collections, things that you can address in the same way at a very general level, which will have different capabilities and so on, but you can, much like files, you talk to them in the same way. DOIP, Digital Object Interface Protocol, which I won't have much time to talk about today, is key to all of that. It gives you a standard interface. If you know how to talk that, then you don't care on what happens at the far right end of this picture. The file system analogy fits in well here. If you think of the right end as different kinds of bit storage and the left end being files. There's lots of ways to get from the bits to the file, but in the end, the user or the developer only has to know that it's a file, doesn't care how it got to be a file. So what's the status of all this? Well, there's specifications. It doesn't require the handle system. I realized when I look at this slide right here, I should have said that earlier. Maybe I should have left the handle system out. It would be any kind of identifier, but that's an example of a well-defined specification for an identifier system. There are others. DOIP version 2 is more significant. This is owned now by the Dana Foundation, the same group that owns the handle system. The key in this context is that it assumes identifiers for everything. So its transactions are basically a set of identifiers and connections between the identifiers, clients, objects, types, operations. Each request is a client invoking an operation on a target, and that target can include servers and so on. Software, there's software available from CNRI, and as I'll show you in a minute, there's software available from other places as well. And of course, when we say handle.net, there's identifier software available from people other than CNRI. Implementations, multiple CNRI project. Disco, which is being discussed, no doubt, in a meeting opposite this one on biodiversity. They use this in the Natural Science Identifier Registry.org. And in general are planning their future projects around digital object architecture. There's a larger biodiversity group, including CNRI and DISCO, but also includes IDIG-Bio and Specify US projects. NIST has a large project going for material science using this stuff. And the thing I was happiest to discover putting this talk together is Peking University has a completely independent implementation of DOIP, which is what you want for that sort of abstract specification. You want multiple implementations, so that was very good news. And last picture on digital object architecture, this is the same, this is that horizontal picture that I showed with the cloud in the middle. Vertically, the earlier picture was idealized model. This is a plan. This is the biodiversity plan. And the reason to show it is to show you, take a look at the bottom where it says existing services continue. The idea here is no one is going to be asked to take their existing data management standards and throw it out. No one would do that. That all keeps happening. Existing services continue, but you add a service on top of it. Digital specimen mapping, we're talking about biodiversity, physical specimens here, and you map those into objects. The analogy here is the internet. When the internet came along, people didn't take their existing networks and throw them out. The internet wasn't the initial network. It was a way to do internetworking. So you took your network and you put a router in front of it, and then you joined the internet. These little gears along the layer of digital specimens mapping, that's the equivalent of an architectural router to get the data. It's a data router in effect. All right, FAIR principles. We've all heard of FAIR principles. Probably most people in this room are fairly conversant with it. The green here is supposed to say what you can do with in the technical infrastructure. I do worry sometimes that people take the word fair too literally and think that mainly this is about making things open and available and honest and pure and clean. In fact, it's mainly, or it was intended mainly to be about automated client exploration. The machine knows what I mean. We need the machines. There's too much data. We wouldn't need machines, the middle quote there I like, capable of autonomously and appropriately acting when faced a wide range of types, formats, access mechanisms, protocols that will be encountered during their self-guided exploration of the global data ecosystem. That's exactly what we want to do. The bottom line there gives you the idea of what we hope that agents, autonomous agents, will do, navigating this world, get information, interpret, decide, get information, interpret, decide, etc. At a low level, that could be just doing extensive search for something at a higher machine learning, artificial intelligence layer, that would be looking for patterns that humans can't see because there's too much data. Finally, the hard part, at least for me, metadata and semantics. The part I know least about, but also which I know is the most difficult. Metadata is essential to all of those 4 FAIR aspects. And this is the machine processing. That means that metadata has to be well structured and must express explicit semantics, especially for the higher order stuff that we hope machines will be able to do with the data. The links and pointers all have to be qualified. That's very important. Human beings can follow a link and say, oh, that's what that link meant. Machine can't do that. It has to know what's at the other end of the link a little bit ahead of time, especially if it has to decide which of 10 million links to follow. That is, we must characterize relationships among objects. That's what qualify means. And of course, it has to be understandable, use a common format. Automated discovery and reasoning will require semantic interoperability. The digital object framework does not specify an implementation choice for structured metadata. So the FAIR digital object framework looks at the semantic web and linked data approaches. And those people were in the room in Paris, and they agreed to that joint statement, which Rob provided a link to. There are, however, some things that need to be done, and they're very difficult things. Minimal set of mandatory metadata, agreed upon ontology. Some people may not even think that's necessary. I don't know, but I know that the people who are working on the semantic side of the FAIR digital object framework believe they have to do that. And I've probably gone too long, which I apologize, but I'll end. I can't resist ending with George Strawn's fanciful IT eras. George was in that meeting in Paris, and he's been in with he was part of the original internet crowd. Now he's on his 4th retirement job, or maybe his 3rd, as head of the National Academy's board on research data information, Birdie. So he's been through all this. So the first era, 1950 to 1995, many computers, many data sets. This is the world of mainframes, midframes, terminals, local networks, and the beginning of the internet taking off. Lots of isolated pockets of computing. 95 to now, a little while from now, single computer, many data sets. This is the notion that the internet functions as a single computer, and our little laptops are the new terminals. Not far from the truth. The old Sun statement, the network is the computer. A geekier version of that is the network is the backplane. That's what we all plug into. So you had a growing universal connectivity. We have it now, but the data stays in silos. So is imagining the last phase, or at least the next phase, single computer, single data set. Increasing levels of abstraction lead to interoperability of heterogeneous data. And if we can do that, or if we do much of it, that I'm confident will lead to quantum leaps in information management and automated discovery processes. That's my talk.
Thank you, Larry. Very, very good. I have not been watching the chat, so I don't know if there are any questions there, but if anybody would like to unmute and ask Larry questions regarding his presentation, please do.
If I may, Rob? Yeah. So thanks, Larry. Really, really great talk. The aspect of the semantics is that's the world that I operate in. I think our paths have crossed on several occasions. Yes. On that regard, like what's happening now is to realize that this agreed upon ontology thing can happen locally, but is unlikely to happen globally. But what has happened, and what's very encouraging my side, is that the developers of these different ontologies are making the ontologies themselves interoperable. So the users or the application developers don't have to do it. And this is happening with ESIP, so Earth Science Information Partners, and the OBO community. And we're cross-mapping the ontologies at source. So there's an authoritative, expert-driven cross-mapping, semantic harmonization clusters. And I think that's an activity that can help greatly so that this doesn't bifurcate and end up in a kind of free-for-all.
That's great. Do you have a pointer of some kind you can stick in there, or maybe
yeah,
it's too complicated to summarize?
Yeah, exactly. So the ESIP semantic harmonization cluster has ongoing activities, and yeah, I'll drop links in the chat to that.
Okay. Is that a middleman sort of notion, or something else? I mean, do things map to some more abstract?
Right. So the two ontologies themselves are like this abstraction layer for semantic interoperability, but they're just developed independently, different communities. Now we're bringing them together through authoritative, expert-driven mappings, but also having automated mappings offered. There's a new standard for mapping ontologies, SSOM from the biomedical world, that's getting some traction there. And I think that's the way, because we won't have enough human resources to do authoritative mappings for everything. So we do need some automated mappings too, using a bunch of technology. But when we do have expert groups, we did this with Global Cryosphere Watch, and we're moving on to like the marine section and soils. When we have experts who understand the field and are actually harmonizing the definitions themselves, we can then implement that in a machine readable way. So that's the objective, to have these different entry points for semantic harmonization to be able to cover enough ground to make it tractable and deployable.
Great, thanks.
So Larry, Bob here. I have kind of a meta question for you, I guess, which is a lot of fundamental advances in science come through a combination of intuition, asking the right question at the right time. I mean, how much of that'll be supplanted by a world of fair digital objects? How much can we expect machines to do independent of our intuition and our, you know, my former boss, Ricardo Giacconi, used to say, you know, the whole thing about science is knowing what question to ask when.
Yeah, that's a great observation. I have no idea, of course, is the answer. my hope is that we learn to ask questions. We take advantage of the machines by continuing to ask those same intuitive questions, but perhaps even at a slightly higher level. So I just had an interesting conversation with someone who described what research they did for their PhD thesis and how this would work in the machine world. But then pushing it a little further, would you know how to ask the sort of higher order questions? I think there might be some connections in these fields, some patterns. Can you tell me if there are any patterns here? And then you get back 6 patterns, and 5 of them are obviously artifacts, but one of them might be something you hadn't thought of, and it would be interesting. That would be my hope. Anything else?
Hi, Larry. This is Maggie Hellstrom.
Hi, Maggie.
Nice to meet you again. I have one concern with all of this. I mean, it's all well and good to have the system that can fully support the automated processing of data, and be it autonomous or instigated by humans. But how do we fit in the concept of quality control in this? Because as has been mentioned several times, I think today and throughout this whole plenary, just because data is fair or has a high fairness score doesn't mean that it is that the quality of the contents of the data is good, or that it is even fit for purpose. And of course, you can trust metadata, or especially if you can annotate with user experiences to data objects or digital objects. You could start to hope to weed out bad apples from the whole thing. Sorry for mixing metaphors, but how do you see the ability of this system to deal with the bad quality information?
Yeah, another excellent question. Of course, I'm not sure I know the answer, but I do think that we will have to develop approaches to do that. if we say there's, I mean, what you make me think of is if we say there's too much data for people to process and we need help with machines, how do we watch the machines? How do we make sure they're doing a good job? And then are there enough people to evaluate the results of it? I mean, we do this in other areas because of all the political polling that's been going on recently. And I used to be in the survey business. That's one thing that occurs to me immediately. I mean, you don't just take the results of a poll, you look at how it came to be. So I think we would want to, especially in science, we'll want the machines to tell us what they did. That's been an interesting aspect of artificial intelligence. Sometimes the artificial intelligence, algorithms can't tell us what they did. In the case of science, we might really want to know that. And that might be another avenue of development and exploration that needs to be looked at.
Yeah, thanks. And I think this also in some part addresses what Bob was saying just now, that we will still need the scientists and or the experts, say in industry, who are dealing with data to really not only ask the right questions, but to be able to check if the answer or the response is at least reasonable.
Yeah, and I think that'll be a change. I mean, we'll have to learn how to do that. Thanks.
Volmar raised his hand.
Yeah, so I have a question regarding the digital object architecture. So you explained it with 5 different pieces, and one of them was the analog to object-oriented programming to define by function and not by format. What does that mean in practice when speaking about the digital object architecture?
Okay, so
is there an example?
Yeah, sure. An example would be a matrix and a computation on a matrix. So, and I say that because someone I know uses that example. I'm not sure I can compute matrices, but I understand it's done. You would just describe that as a function, and you wouldn't care about the implementation of the function, whether it was done in Python or whether it was done in some other fashion. So you define a function on an object. The simple functions would be, show me your data, or tell me, go to this well-known service over here and then get me the answer back. It would be that sort of thing. So it's similar to object-oriented programming. I don't need to know how the function is achieved. I just need to know the correct input on my part and what I expect back.
All right, so is it similar to how HTTP is defined on top of the other stacks down to the IP? Or, I mean, where does it fit in the analog you had to the internet?
Where does it fit into that analog? It's at a slightly different level because it's those requests, those functions would be carried in the protocol. So the request for the function would go across the wire, if it's a wire, according to a certain protocol, and the answer would come back according to that protocol. But the operation itself, there would be some fundamental, I didn't go into all that, but in DOIP, which is fully specified, there are a couple of core operations, create, delete, that sort of things, the CRUD, plus an important one, which is tell me what operations you have. And then there's a method to extend the operations. So for certain objects, there would be operations that would be relevant to them and no others. So if my object was a survey, back to my former thing, if the object was a survey instrument and the results of a survey, I might ask the object that contained the instrument design, to be the questionnaire, to tell me its skip pattern, and it would tell me its skip pattern. And I wouldn't have to, I wouldn't have to understand the format of it and say, show me the places where this markup exists. I would just ask for the skip format.
Thanks.
Okay. Anything else?
Thank you, Larry. Very informative as always. But even if there are more, I would ask that you take them either up directly with Larry or ask in the chat as we go forward. And we'll move on into what Rainer has prepared for the landscape survey.
So thank you very much. First of all, Larry, I just assumed that we can have your slides to put it on the webpage.
Sure, I'll send them to you, Rainer.
Oh, that's great. Secondly, I must admit, I had my first task here in the DEFI group to push the button for the recording, and I missed it in the beginning. So Rob, sorry I missed your talk, but I pushed the button during the title slide of Larry's talk, and since this time we are recording. So I would like to ask you now to do some interactive work. I'm just trying to share this one. So I think you see now my slide and you see here a question. Which are the required technical components? What do you think? What do you think to utilize fair digital objects in science? This is not a task. We are just looking for ideas and so on. And we are collecting in the Google Sheet, and the link is also in the chat, for a couple of minutes, your ideas. If you could please log into the Google Sheet, and I see that most of you have already registered in the attendee list. From page 4, we do the survey of the landscape. And please, for a couple of minutes, put in your ideas and we will collect them. In the meanwhile, Sabrina, Felix, Andreas, and Thomas are working in the background, and they are trying to collect and to summarize the results which we are collecting now at the end of the session. So take your time, just a couple of minutes, and put in whatever you think what might be important. So we see that the answers are getting in, that the table is being filled. It'll give you a couple of more minutes. Well, thank you very much. Thank you very much for the huge amount of ideas which I see are being collected in the notes. Now for the discussion, I would like to ask a second question. Sometimes it seems for the users, so for our scientific communities, it seems to be difficult to utilize fair digital objects. And this is exactly one question I would like to ask here for an open discussion, not to write it down in the collaborative notes, but just as an open discussion. What do you think? What steps are the easiest or even the hardest to get the fair digital object concept adopted in your work, in your scientific work? Please just raise your hand and then we can start discussing. Françoise.
I have a question about your question. You know, you are asking the question mostly to people who provide services, do you? Not
Yep.
to the scientists themselves. And I hope that in the end for the scientists, it will be not much more difficult to use everything, otherwise it's dead before beginning, in a sense. So I understand how the hourglass is supposed to make everything simpler, but when I read the table, I have the impression that it will make everything more complicated and more strictly controlled and so on. Am I right or wrong?
I would say currently, this is really the danger that the amount of services which are required make it difficult. But most of the services and the functionality of the services should be hidden to the users. Maybe
I am also, sorry, I am thinking about the users, but also to the service providers, because they are also users of the system.
Mm-hmm.
And what I see in the table seems to make their life much more difficult, but maybe I'm wrong, because what Larry was saying is that it makes everything easier in a sense, but I am not completely sure.
So Francois, this is exactly why I've targeted gateways or VREs for implementation here, is that, you know, it can be a side product of what's already happening within the researcher's workflow, right? So they go in, they drop their input data in, they run a Gaussian application on it, get some output data. These all then are treated from the beginning as digital objects. And so it's basically part of the natural workflow that they would go through, and at the end of the workflow, what they get is a digital object that describes the entire workflow. So I think gateways or virtual research environments are a nice way to, or an easy way to introduce this to the researchers, simply because it's putting it in their own environment, and it's almost as if doing what you were doing, but here's a bonus at the end. It's all fair, right? It's all been treated as fair digital objects. Here's all of your history. Here's where you're registered. Here's how you can find it outside of the VRE or the gateway. So I think to answer, I guess, Rainer's question, or Reiner's question, is the easiest way is to embed it in what they're currently doing, right? And then showing the advantages of it during the later steps of publication, or when they want to collaborate or communicate it to someone outside of the experiment that they're working with.
And then the question goes, what is the overhead on the service providers and the data providers?
So the overhead on the service providers is once you have the services set up, it's relatively minimal, right? They're just using the services that you have set up, but you do need to run a digital object architecture set of services, and that overhead we found it to be relatively minimal using one specific set of software, and that's the data type registries, the Cordra software provided by CNRI, and the handle service. Now, I can't say anything about others, but there is some infrastructure service and effort needed to maintain those services. The overhead on the data providers, in the case that we've done with the adoption project, has been zero, because the input data is giving a or is only starts being treated as a digital object once it starts into the workflow. I think that it should be a digital object before that, but that's a place we haven't experienced yet, and there would be some overhead, right? So you'd want it as a digital object before it ever started in the workflow, ideally. Where it lives in the repository, it should be treated as a digital object, and that makes it actually even simpler for ingestion into a workflow. So I don't have a firm answer on the overhead for the data provider.
Maggie, you're next.
Yeah, so I think that the hardest thing here is to get the resources allocated for this construction of this intermediate layer that is needed to, so to speak, FDO-fy already existing services which have their own APIs, often RESTful ones, which do not follow exactly the same logic and etc. I mean, it's not the one-to-one correspondence, just translating posts and gets and deletes, etc. You have to put some more work into it to fit it into the DOIP world. And I think that organizations or larger projects or infrastructures that already have this in place, they are very hesitant to spend this effort to even just implement this. So that's one thing. And the other thing this is really targeting now data intensive research, if we are staying in the academic world for a bit. And those who are doing that and have been doing this kind of science for the last decades, I mean, like people in genomics or particle physics and the like, they already have all their processing set up to work with existing APIs or existing workflows. So they too will have to invest quite a lot of effort, I think, regardless of whatever you say, Rob, with your very successful rapid implementation test. But I think out in the wild, this is much more difficult. So there's a lot of inertia here. So we really need very, very easy instructions for how to do this. We need clinics where people can bring their services and have them adjusted with the help of expertise, so that it goes fast and doesn't introduce errors or misconceptions or even errors. I think that's really the hardest thing.
Thanks. Carsten? We can't hear you, Carsten.
Sorry, better now?
Yeah.
So this might be a more naive observation, but I think that FAIR is well understood as well as it's well misunderstood. And I think what is needed also to get the concept adopted is to reclaim the FAIR agenda. There's a lot of discourse, and the FAIR discussions are perhaps, I would say, more laissez-faire now than ever before, talking much more about repositories and the like. And I think that what is being done right now, as far as I can see, is building much more to the bottom of Larry's last slide, that it's actually building on the top of it. So to reclaim the FAIR agenda, or start talking about these two ways of working, because I don't think that we are working in this, what I would call hardcore FAIR way in many projects.
Thank you. Pierluigi?
Thanks, Rainer. Yeah, so 2 points on that. It's for adoption, firstly, it's the trust that it's actually worth it. So for the note taker, I've already typed it in, so it's up there, don't worry. So the trust that it's actually worth it. Like, where are the implementation examples that show this is worth investing in if I'm an infrastructure or a project or a program? And that has to go beyond one siloed use case where it works beautifully. It needs to work across a couple of things that are doing things very differently to show that it actually accomplishes that sort of interoperability. And I also acknowledge this is a chicken and egg scenario. Like, a lot of us have faced this in our work. We need the adopters first to build that interoperability. But that's what we have to do. We have to identify who's going to pioneer this, who's going to take the risk and show that it works. Disco, maybe with partnering with others that are trying to implement this, maybe the way forward. But they have to be willing to collaborate and say, yes, we acknowledge we do things differently. We're not going to use the same tooling, but we still have to make the projections of this thing work together. If that's not the mode, then we face what happens typically, competition for use this tool, use this workflow. It gets really boring really fast, right? So that's not how the web works, and that's certainly not how this FDO ecosystem will succeed, in my opinion.
Yeah, and that's been definitely one of the biggest challenges we've had with the rapid testbed, is that we've had a lot of interest, but people really stepping up to provide the effort to attempt an adoption. We've really had to move to them, and we've had a limited number of cases where we've been able to do an implementation.
Right. I think maybe, like, again, a really minimal example, like, proof of concept example of it working may work. In our UNESCO work in this ocean data information system across multinational data stores, again, we're going first the minimal way to get a foothold in there to show that it's possible, and then to get their program managers to invest in greater interoperability. So something strategic on that layer may help.
This is exactly one of the objectives of this group, to bring together here not only the developers, but also the adopters, and to create these kinds of minimum sets.
Yeah, absolutely. But also, even not just the adopters, but let's say the funders, the strategic people, because they want things to be more efficient. They are tired of investing in large infrastructures that don't talk to each other. So, there are people who are interested in this, and it's a question of connecting to them too. There are networks, of course, that we can activate, but there has to be something ready to show. Otherwise, it's just another idea.
Yeah. Zachary, we can't hear you. So, Volmar.
All right, so you've already touched on this a bit, I think, but it's really a question on kind of who gets to decide which vocabulary and definitions you use for these digital objects. And I mean, being in a world where there are very few implementations, there is very few people represented maybe in some of these ontologies. And I mean, how do we get more people to get involved in contributing to these ontologies? So, I mean, making sure that there is full representation and acceptance for using these definitions. I mean, both within a specific domain and also maybe across domains that are kind of related in some sense.
If I may comment that, I think this is exactly one of the core objectives of RDA, to try to build a consensus how to handle things and to find adopters, many adopters who are using the solutions. And the success stories come from the adopters. So if we are providing a consensus or on a couple of specifications and nobody is using it, so it's useless.
Yeah, and I mean, just to add on that, I mean, we are here in the RDA, we represent people who are really interested in data. We talk about research data. Some fields don't talk about research data, or they put another label on their research materials. So, I mean, just making sure that we catch people who are not involved in these contexts where these ontologies are defined. And make sure that we are inclusive and don't kind of exclude excellent researchers just because they don't move in these circles.
Sure.
I think, if I may, Rainer?
Yep.
So on that point, yeah, I totally agree. It's always a function of who's at the table, who has the opportunity, who has the knowledge. I mean, there are entire communities who do excellent work there who are not connected to RDA. They don't really care about it. And the question is then, how do we make it interoperable? And also, you know, as you said, there's very good research examples, but we also have to distinguish between what's a research grade ontology, an idea that's published, versus something that's operational, sustainable, that goes through continuous integration checks. You know that it's a product you can rely on to build data architecture, right? Now, we also need, I think RDA's mission would be great to help those innovators get connected with the operational space, get due credit for what their contributions are, and have that sort of on-ramp from innovation to operations, because they're different businesses, they have different business models. But if we build a bridge, we can start to sort of streamline this thing.
Let's try Zachary again. Okay, Jonathan.
I apologize that I didn't know I was called. The sound on my end is very choppy. So the challenge I wanted to bring to the table was one of granularity and mapping. And just to give a simple example, bench scientists frequently do their work in spreadsheets. And I think in some cases, a single spreadsheet might be best represented by a single digital object. But in other cases, a spreadsheet could be describing many digital objects. And I think it's a challenge sometimes to choose the appropriate granularity and to do the mapping back into the format that the bench scientist is comfortable working with.
Mm-hmm.
Yeah, and in the end, the granularity is pretty open. I've spent a lot of time thinking about this early on, and really from the infrastructure side, the granularity is going to be determined by the application and what the application is designed to intake or output. So I agree with you. Granularity is one that's up in the air, but it also needs to be coupled with the analysis steps and the computational processes that the data will go through.
And like from a development example, like often we start at in developing community ontologies, we've surrendered branches of our ontology that we're getting like out of our scope. We look for somebody to adopt it, and then again, it's an interoperable product because it's cross-linked to an existing thing and uses the same architecture. So I think again that cultural change of let's say, look, this is too big for us to handle. Let's get somebody who can run it at that granularity, take over, train them, etc. So that works, and people are interested.
Mm-hmm. Jonathan, you raised your hand.
Yes. Hi. Can you hear me? Okay. Yep.
Yep.
Oh, good. So I just wanted to reflect on some of the things that so this is Jonathan Clark from the DOI Foundation. And I think I've mentioned this before, but we have had over the years a lot of discussion between different users of DOI and different applications on how to be more interoperable. And we usually say, well, okay, let's look at a use case. So we've got some good use cases, but when it comes to deciding whether to do it with, say, data typing or to move more towards digital object architecture, it's always seen or has been up to date as being a bit too complicated. There's always another way to do it. And so currently the interoperability that we've managed to stimulate has always been done through some other mechanism, through some other way, some other sharing. And I really think, I looked then at the Disco example, and they truly believe that digital objects, and they're pushing it without really, there's some use cases, but the use cases are largely theoretical. And so we've got this catch-22. If you want to make interoperability now between 2 or 3 applications, there's probably a easier, simpler, cheaper way to do it that doesn't use digital object architecture. But we all know that in the future it will be more sustainable to do so. But the sort of the lure of the simple, quick solution dissuades us from the longer term. And it's this thing that we come across, and Larry will know this too, in the DOI Foundation. And I don't really know how to break through that, other than to do what you're doing, which is to highlight the deployers of it and to showcase them and hope people get the idea. I'm not sure that's helpful for everyone, but it just strikes me as there's this catch-22 in all of these discussions.
Thanks. Looking at the time, I think we have just time for one other remark question. Christian. I can't hear you.
Can you hear me now?
No.
Yeah. Okay. Yeah. So this is Christian Busse from German Cancer Research Center. So one thing that I've been missing a little bit is how we integrate code as a digital object into all of this, because most of those things that we've been talking about were data. There are clearly properties that also would apply to code. And from what I've heard in the talks, there are also apparently some code components which are assumed to be packaged with the data. And I think it's important to make sure that if there is only one digital object as the central atom to deal with, then it needs to be able also to deal with code objects and their additional properties that need to be covered.
I think this is quite simple because a digital object can contain any kind of data, including software code, including artifacts, including metadata, and so on. So it's a wide range.
And what is important there is that you have a metadata profile that is designed to handle code versus some other type of data. So the mechanism is there. Does it need to be explored and fleshed out? Absolutely. What are the proper kind of high-level things that you need to know about the code and that need to be captured in the metadata? But the mechanism with it having a type registry and a type profile is there. But I agree that the software needs to be treated exactly the same, though, or as a digital object and exactly the same as other digital objects, though the metadata profile will differ in several ways.
Okay.
So now going back to our table of technical components, Thomas, are you ready to present or to summarize some of the results which you found?
I am ready, and I can try to hurry a bit to manage it just in time. So, well, for all of you who might wonder what we wanted to do with the table you filled in, what we did is we took out the entries, put them into another table, and tried to group them somehow and put them into categories, just in order to get an overview on where might be priorities, which might be the most interest in the audience. And I want to share with you this the outcome of this work. I hope you see it now. Just as a short explanation, on the left-hand side, you see Survey of the Landscape. This is the top category containing all the elements. So altogether, we have 22 contributions. In the next column, you see the categories which we defined in beforehand. So they might not be perfect, they might not match in any case perfectly, but this was the selection of categories we had. And on the right-hand side, you see the services or components, or however you want to call them, which were part of the table in the collaborative notes. As an explanation, we see that the ontologies have a quite relatively huge number of mentions in the table. Parts where fair digital object framework for adding some kind of semantics, ontology mappings we had, and semantic handling technologies. On the tools side, we had fair digital object editors, clients to communicate with fair DO infrastructures, search facilities, and tools for validation.
And well, so you will see a couple of categories and the according services you mentioned. I think what we will do now is we will go again over the table. We'll check again the categories, maybe change the category in which the one or the other service was added. And then we will find a way to make this table available online. We'll send you the link. And probably we can discuss this outcome in the next Data Fabric session.
Mm-hmm. Thank you, Thomas. Definitely, we will include this kind of table, as a summary table, into the collaborative notes. And we need to discuss the outcomes and the collections and maybe the missing and the gaps also in our next virtual session. Looking at the time, the question now comes, what will we do next? And for that, Thomas, could you please withdraw the screen sharing? Thank you. So what will we do next? Most of you might know that in the IG Data Fabric, especially in the context of fair digital objects, we have monthly meetings, one in the morning, UCT, and one in the UTC, and one in the afternoon. So to cover both time zones. So in our next regular meeting, which would be in November, but since we have this virtual plenary now in November, maybe we will skip that one. And the December meeting would take place on Christmas Eve. So I think we don't expect many participants for this day. So the next meeting would be on January 28th. We have our monthly meetings, and I should have said that, on every fourth Thursday of a month, and then we have to, span both time zones, the Eastern time zones with the morning session and the Western time zones with the afternoon session. But of course, everybody's invited to join both sessions. So we will discuss the outputs of the table, the discussions we had today. Thank you very much for all of your input, for your contributions, and for the lively discussions. We will discuss it in the next meeting. And so I will give back to Rob for some last words for today.
It strikes me that we had at least 3 people bring up chicken and egg examples for different portions of this, and I think they're exactly right. We have something there, and I actually would like to bring up a fourth, is we need the effort, funding, investment to make these things happen, right? Which is the big one that we've had some success in doing smaller projects and some success moving forward, but we really need an investment from someone to actually make this infrastructure at a production level to be utilized widely rather than at a testbed level. So I did want to say that and just kind of add in a fourth one there, that the funding investment chicken and egg problem is there. I think we know where, to move to another analogy, I think we have an idea now of where the treasure is located. We need an investor to pay for us to dig it up, right? Finally, I will say volunteers for co-chair, please contact myself or Reiner, or if you want to nominate somebody for co-chair of this group who you think would do really good in helping direct this conversation and be part of this group, we're taking those and we're open and we're past time. So I'll end it there. Thank you everybody for attending. Thank you, Larry, for coming to talk to us. And I think we got wonderful input in the table. And thank you, Thomas, for compiling that into a table for us. I think that's going to be hugely helpful moving forward. And goodbye.
Well, thank you very much. Goodbye.
Bye.
Ciao, thank you. Great session.